Hey everyone, so continuing for standardization, we have one of the examples where we are given that x follows a normal distribution with unknown parameters mu and sigma square, but we are given two particular probabilities where the p bigger than 5, where x is bigger than 5 has a probability of 0.25 and when x less than 1 is 0.1. So intuitively, you know that the mean must be less than 5 and more than 1. Why? Because for the probability to be 0.25 bigger than 5, it is somewhere around here, right? This is something about 0.25, so it must be beyond the mean, and 0.1 is right here, and it's 1. All right, so it must be between 5 and 1, but nonetheless, let's get right to it. So because we have unknowns mu and sigma square, we cannot just use inverse norm. We can't even use equation solver because there are two unknowns, the mean and the standard deviation. As such, we have to do standardization. Alright, so we standardize this, you then have pz now, and basically standardization minus mean over sigma equals to 0.25. From here, similarly, z less than 1 minus mean over sigma, and this equals to 0.1. Then from here, we can now apply our inverse norm because we now know the distribution of z, which is 0,1, the standard distribution. As such, we do standardization to get the following values, which are right here. But we do inverse norm, we get, for the first one, we either do 0.25, 0.1 right, basically because we are looking at the area on the right, because the probability is bigger than a particular value that is 0.25, as such is the right area. For those using the older GC, the one without the option to choose left, right, center, personally the better GC is instead you then key in 0.75 instead, because for the older GCs, you are calculating the area from the left side. Alright, you don't have the privilege of using the right, left, center. Well, personally, I don't like to use right, left, center because it's kind of a hassle. Alright, so either one of these works, you notice that this would then give you the value of z 0.25. Cool. And then the bottom, well, since you're doing the left area, regardless if you're using the old GC or the new GC, it will be 0.1, which is minus 1.28155, and so on and so forth. Therefore, we then have 5 minus mu over sigma equals to 0.6744897495. You can just simplify this to 5 dp or 5 significant figures. All right. Now, why does this work? Because of the standard distribution, right? You know that the area is 0.25. Then you know that this particular value here must be the variable at this point here. So let's say this point here is z1, because the standard deviation, the standard distribution graph, standard normal distribution, has a value of 0.6744897495 to give an area of 0.25. So that is why we can equate it like this. Then of course we have the second equation, which is simply 1 minus mu over sigma equals to minus 1.281551567. Now we can be able to get a simultaneous equations, because after we simplify this, we then get 5 equals to 0.6, oh, here we go, sigma plus mu, and then the bottom equation, 1 equals to minus 1.281551567 sigma plus mu. Then we can then solve for sigma and mu, because we now have a pair of simultaneous equation with two variables. So very simply, we then key into the system of equation, like something like this. You can either key in the exact values or simply use the inverse norm from here when you key in the different values for our y. So in this case, y is sigma, x is mu, and either you key in this whole thing or you just key inverse norm from here. All right. Then from here, you just click on solve, which is, well, not a difficult thing to do. And you'll get the answer as shown right here. Mu is 3.62, and sigma to 3 decimal place, or rather to 3 significant figures, is 2.04. All right, so that's how we do standardization, using the idea of finding and rather converting to a known distribution, in this case a standard normal distribution with mean 0 and 1, and then using inverse norm from there. So there we have it, standardization in the context of simultaneous equations.